Welcome back, everyone. Our next speaker is Chi Gua, and I'm excited to introduce Chi. He's a PhD student at Harvard University, advised by Todd Ziegler, and his research involves combining optics and computer vision algorithms to create computational sensors. Chi received his bachelor's degree in automation from Tsinghua University. He's interned at Facebook, NVIDIA, and Baidu, and has also received a number of awards, including the Best Student Paper Award at ECCV in 2016, and the Best Demo Award at ICCP in 2018. We're excited to have Chi join us and look forward to his talk. Take it away, Chi.
Thank you so much, David, for the introduction. Hi, everyone. I'm Chi. Today, I'm trying to promote a rapidly maturing technology for optical manipulation, the Metasurfaces. I know some of you have already started using this technology already in your research. I thank my wonderful collaborators. In particular, I'd like to acknowledge Dr. Zhu Junshi, who has contributed significantly to this talk. I will first give a brief intro to the Metasurfaces, what their advantages and disadvantages are compared to traditional refractive and diffractive optics. Then I will show you some potential applications of Metasurfaces with an example of my past research. We have been making lenses for quite a long time, from the Nimmer lens 3,000 years ago to the medieval glasses and to modern optics for microscopy and photography. These engineered optics have been more accurate and compact. Inspired by the semiconductor industry, where scientists and engineers build nanostructure that manipulate electrons, people use similar fabrication techniques to build nanostructure on a surface plane to manipulate photons. These surfaces with nanostructures are usually called metasurfaces. The shape of the nanostructures on the metasurface determines how photons are manipulated when they travel through. By designing an array of such nanostructures, the electromagnetic field that passes through the metasurface can be modulated to the desired wavefront. We can design the metasurface to be a focusing lens or metalens by designing the nanostructure array so that the phase delay added to the wavefront is quadratic. There are several advantages of using metasurfaces in your setup. First, it can achieve similar or even better imaging performance with much smaller size than the traditional optics in the design wavelengths. For example, the metasurface in this image on the left has the same numerical aperture and similar diffraction limited spot as the commercial objective lens on the right at 532 nanometers. Second, metasurfaces can provide versatile wavefront control. By designing specific shapes of the nanostructures, we can achieve tailorable modulation on the phase, intensity, polarization, dispersion, and incident angles of the incoming wave. Third, metasurfaces provide incomparable multifunctionality. For example, we can design metasurfaces that do spatial multiplexing of different modulation function, or design different modulation functions for different polarization, or wavelength, or incident angles on the same piece of device. A similar device to the metasurface that people often use is the diffractive optical element. Here is a comparison of these two different types of devices. One apparent difference is that the structure of the metasurface is generally smaller than the DOEs. Fabricating custom designed DOEs are very convenient these days. People can build DOEs simply by 3D printing or laser writing if higher fabrication precision is required. Fabricating the metasurface requires similar procedures as fabricating the semiconductors, which involves clean room operations like electron beams lithography, ALD, and etching. There's already a startup called Metalens that tries to commercialize the metasurface technology. In fact, they just launched their first product in June. Besides the fabrication, metasurface and the DOEs have some differences in the light modulation capability. As shown in this table, metasurfaces can modulate more than phase and amplitude of the light. So, if you plan to use metasurfaces in your prototype, several things that you need to consider are whether you and your collaborators are accessible to the clean room facilities, the cost of the clean room, the lead time, and whether your application will benefit from these advantages of Metasurfaces. Now let's talk about applications of Metasurfaces. I have mentioned this startup that commercializes Metasurface fabrication. Their first product launched this year is a very small and simple dot pattern projector called Orion. It consists of a laser emitter and a piece of Metasurface that modulates the illumination into dot patterns. This product can potentially be used on phones for Face ID kind of applications. What is more, I personally believe that Metasurface can be widely used for visual sensing. An artificial platform usually consists of two parts. The first part includes some optics to transform light signal from the environment to the digital signal. And the second part has digital computation to recover desired scene information. A lot of computational photography people like myself are trying to migrate a large portion of computation to the optics acquisition, so that the optics act like an autoencoder. The photon transducer no longer receives an image anymore, but a feature map. The digital computation starts from this feature map to recover scene information. I call this process of perceiving scene information via the synergy of optics and computational visual sensing. These computational visual sensors have been widely used in modern applications ranging from gaming to autonomous vehicles to reduce their size and computational cost. And they have the possibility to be used on future applications which have strict constraints on space and power. And it is very difficult for current methods to be deployed on them, such as micro robots, wearable devices, medical imaging devices, and so on. As Metasurfaces has the advantages to be compact, versatile in wavefront modulation, and multifunctional, I believe they are very suitable to be used as the optics part in computational visual sensors. Several groups in this community have already pioneered their research in incorporating Metasurfaces. And today I will present a past work from our group, which is an example of using Metasurface to build a compact single-shot depth sensor. The work is based on a depth sensing algorithm called depth front differential defocus developed by our group. By using this algorithm, we can estimate a per pixel depth and a confidence estimation of a given scene from two shared perspective, differently defocused images without active illumination and with very cheap computation. Here, the depth is masked according to the confidence, so that only pixels with confidence higher than a threshold are shown. In our previous setups, the two images are captured sequentially, so the object is assumed to be static during the capture. We'd like to design a new optic that captures the two images in a single shot. The idea is to design a metasurface that simultaneously forms two off-axis focal spots with different focal lengths for a single point source. This can be done by separately designing two metasurfaces, each acting as an off-axis focusing lens, and interleaving the nanostructures of the two together. For each of the off-axis focusing metasurface, it will add a quadratic phase delay to the incoming wavefront. So to design an array of nanopillars on a metasurface that generates a specific wavefront, there are usually three steps. First, we invent a library of sub-wavelength nanocells. Each of the nanocell has certain shapes of nanopillars. For example, in this project, we use cuboid nanopillars. Our library consists of cuboid nanopillars with different width, W. And then we use the electromagnetic field solver such as the FDTD, to simulate the EM field of each nanocell given different incoming waves. Third, based on the simulation, we can draw the mapping between the phase delay and the width of the nanopillars so that we can pick nanocells from the library and arrange them to generate the specific phase delay via the inverse mapping. In this design process, we assume there to be no interactions between wavefront at different nanocells. Here are the SEM images of the designed metasurface. Using this metasurface, differently defocused images can be simultaneously created on the photosensor. To avoid overlap between the two images, we add a field stop in front of the lens. In fact, this field stop can be avoided if we design a polarization selective metasurface so that the two images will be of different polarization, and we can use a polarization sensor to separate them. Interestingly, this design is inspired by the eyes of jumping spiders. They use layered retina to capture two differently defocused images, while we use a metasurface to do the same thing. This is the first single-shot metasurface depth sensor. The optics only include a 3mm diameter metasurface and the photosensor, which can be made very compact. Here is a quantitative analysis. The x-axis is the true depth, and the y-axis is the predicted depth. The width of the color band is the mean error. Different color represents different confidence threshold. With confidence higher than 0.5, which corresponds to 50% density in this case, the working range is from 30 to 40 centimeters with less than 5% relative error. Here are some results. The first image is the scene, and the second, the third are the defocused image pairs. The fourth is a sparse depth map masked by the confidence. All the depth maps are masked using the same confidence threshold. And this is a textured plane that is slanted. To mimic the jumping spider, we use the sensor to predict depths of fruit flies. And here's a video of real-time depth generation. It can run at 100 frames per second. These are dead fruit flies, and these are living ones. This is a depth map of a water stream ejected from the needle to the sensor. The sensor is viewing from the front. The water stream goes up and down. So the left part is farther and the right part is closer. And here is a video of it. The water stream is moving very fast. So the capability to estimate on a fast moving scene like this is only possible for a snapshot depth sensor. Here is a depth map of the candle flame. The three candles are placed at different distances. Here is a video of it. Because the sensor is monocular, it can use any intensity change as depth cue. Imagine if you want to do time of flight or structure light on these non-solid objects, it just won't work. So to conclude, it is the world's first single-shot metasurface depth sensor. It consists of very compact optics that can be assembled in a very small form factor. It requires no control power for optics. The disadvantage is that the current prototype only works for a small working bandwidth of light. Looking forward, I believe there are numerous exciting research projects that involves metasurface and computational visual sensing. First, I have shown an example of using metasurfaces for depth estimation. There are so many other scene information that can potentially be recovered using metasurfaces, such as polarization, spectrum, phase, and so on. And following the recent trend of end-to-end optimization, metasurface can be also designed by joint optimization of optical parameters, M, and the computational parameters, phi. The joint optimization requires a parametric and potentially differentiable model of the metasurface. This requires a differentiable model F that solves the Maxwell's equation given the environment pi and the metasurface shape M to simulate the signal captured on the photon transducer I. So one research question here is, what would be a good model F? People have used numerical solvers of Maxwell's equations such as FDTD or RCWA. These physical methods are accurate, but are usually slow in computation. Recently, people have also developed computational representations of implicit functions. For example, the siren that can be used to solve wave equations. I'd love to know if it is possible to go a step further, that we can have a non-iterative feed-forward computational model F that is differentiable and cheap to compute. Please do let me know if there is already one. There are two reasons to develop a fast approximate model F. The first is due to the increasing complexities to represent the metasurface shape M. In the early years, people have tried simple shapes of nanopillars, for example, the cuboid nanopillars. In this case, the space of nanostructures can be characterized by a single parameter. With more complicated nanostructures, the number of shape parameters increase. Recently, people started to design these free-form nanostructures and even stacking multiple layers, and the shape space becomes much, much larger. When the shape space is large, it is more unlikely to find the nanostructure that generates the desired modulation to the wavefront, but it is more difficult to pre-compute the modulation of each possible nanopillars, as we did for the depth sensing project. Therefore, a fast differentiable model F is much needed so that the modulation can be estimated on the fly. The second reason is that people have been trying to solve the EM field of larger areas of the metasurfaces instead of dividing them into cells and assuming no interactions among cells. As I said previously, in the past, people divide metasurfaces into sub-wavelength nanocells and only solving Maxwell's equations for each nanocells individually. Now, it's possible to make the nanocells as large as tens and hundreds of wavelengths. If we can further reduce the computational cost of solving Maxwell's equations, we might be able to directly solve the EM field of the whole piece of metasurface that is millimeter or centimeters large. Being able to model larger and larger metasurfaces can significantly increase the design space and potentially build metasurfaces that are more powerful and for sensing and imaging. There are many interesting and fundamental problems to be solved for using metasurfaces in visual sensing. I'd like to invite you to join this emerging research trend, and I will be happy to take any questions.
Thanks, Chief, for this great talk. I agree. I think these metasurfaces are really interesting and promising technology, especially for computational imaging. We have a couple questions from the chat. So maybe we can go there. The first question is from Regina Eckert, and who asks, what is the maximum size of the metasurface, and how does that relate to the field of view or resolution constraints?
That's a great question. So, currently, when I collaborate with the metasurface fabrication group here, the maximum size we do is 3 millimeter in diameter. But I believe now, people can definitely make larger and larger metasurfaces, but I'm not sure about the specific number regarding to it.
And does that, normally you think of how the aperture size relates to the diffraction limited spot size or the resolution. Is that the same with metasurfaces, or is there a trade-off there as well?
I think it's the same here.
Okay. Next question is from Barmak Heshmat. He says, great talk. Does this only work with coherent light? Are there crosstalks between different images? Referring probably to the two depth map, the two differential defocus images you capture. And is there a translational shift between the two depths?
So
are they offset somehow?
Okay. So for the first part of the question, so we assumed it's like the scene is like incoherent light source. So we only assume coherent interference from the wave that comes from each single point, and we do not assume like there are coherent interference between different point sources in the scene, so that the two images formed here, like I don't think there are a lot of I wouldn't say like there is no crosstalk, but there is no significant crosstalk that will affect the results. And in fact, we put like an aperture here to limit the field of view so that each of the image will not like overlap with each other. And could you repeat the second part of the question again?
The other part is for these two images you capture, I guess they're each of them integrating light across the whole aperture. So they're not shifted at all or offset? Are they directly aligned as well? I think that's what Barmak is asking.
Okay, yeah, so the two images are using the exact same part of the aperture. So they are all using the whole part of the aperture, because how we do it is by spatially interleaving different nanocells together, so that the two camera modulation function is like interleaved together, so that you can think of the two images to be like exactly the same. We actually don't do any kind of further alignment between them when we process them to get that.
Got it. Okay, well, thanks again for the great talk, Chi, and we'll be back with the next speaker in just a moment.